Thanks to the organizers for giving me the opportunity to speak here. There has been a really wide range of topics, which made me realize that we all kind of go in different directions. So I modified my talk so that the goal is to kind of attract you to ask me questions or answer my questions rather than to point my theorems. So at the end, maybe I'll tell you something that I did, but please feel free to stop me at any time because I'm not trying to arrive anywhere. Okay. So here's the plan of the talk. There will be kind of two sections that are I call them section one prime, because really just trying to get you to catch an analogy. So the first one is an introduction to relative Langlands in the sense of EZSV. So that stands for Benzi Saccharomyces Venkatesh. In the second part, I want to tell you a little bit about the moduli space. And the only thing I'm asking is for you to notice structures that kind of appear on both 1 and 1 prime. And finally, I will tell you about some old and new computations if I get there, that are inspired by these perspectives and structures. Okay. So let me start with relative Langlands, but before that, then we start with Langlands. So the starting data you need is G, a reductive group, over a global field F. And from this, roughly what we want is something like a matching between automorphic forms G. So these are just essentially functions on G that are eigenfunctions or a big algebra of operators. And we want to match them with something like homomorphism. So they're called L parameters. What they are really just homomorphisms from the Galois group, the absolute Galois group of F, the same global field, into the Langlands dual group of G. Okay, so this is roughly what is global Langlands correspondence. So let's just pretend that we have such a correspondence. Then one might ask, what are questions you can ask on both sides that have the same answers? Okay. So let me start on the automorphic side. Then a very natural way to get measurements on the left side is to give an integral. So let's say I give you the data of a subgroup, and maybe I even give you a character of H. Then I can consider the following gadget. So it's a distribution on automorphic forms, which just takes my automorphic form and I integrate it over H times the character. So that's a number. And meanwhile, on the other side, I can give you rho is an algebraic representation of the dual group, finite dimensional algebraic representation. Then from that data, I can make the L function. L phi rho S. So phi is the L parameter. Maybe I should write it this way. So this side sends an automorphic form to a number, and this side also sends an L parameter to a number. And whenever I say L function, I will always think of it as an Euler product. So it's gadget, more or less. P. So one way to very quickly say what is relative Langlands about is essentially asking when do these numerical measurements match up? So it's a very decategorified way to say it, which is also, I think, very, very nice.
Have an S on it. You don't have a S parameter on the left-hand side.
So you can think of that S parameter as related to the chi. So chi might range in a continuous family.
H is
a subgroup of G. It doesn't have to be. So it could be reductive, or another typical case is you can take a Fourier coefficient.
And the right here really means row of phi of the Frobenius.
Yeah, thanks. Rho of phi. Thanks. Okay. So if you've never seen an instance of this working perfectly, let me give you two examples. So the first one is due to Hecke. So he was working in the context of modular forms. So to make that happen, to set it up with groups, let me take these PGL2. And F is a automorphic form. Well, let me say like a eigenform. So in other words, I can think of it as a modular form on the upper half plane. And let me not worry about weight and level like this, because I'm just giving you an example, heuristic calculation. So what he did was, if this is the upper half plane, he takes the modular form and he integrates it in the imaginary axis. So he considers the integral from 0 to infinity, iy times y to the s, with the Haar measure on the imaginary axis, so dy over y. And essentially, he only applies two things. So the ingredients going into this, the first is Fourier expansion. Which is not so difficult. It's just because your function is periodic in this direction, so you can Fourier expand in that circle. And the second thing that is hard, which also bears his name, is the multiplicative properties of the Fourier coefficients. So this allows you to turn basically an infinite sum of the Fourier expansion into an infinite product. Probably that's what's going on. And well, he answers the integral in terms of, write like this. So here, this is the L parameter of your modular form. And this is the two-dimensional standard representation of the dual group, which in this case is SL2. Are there any questions about this?
Rho and S have swapped places.
So yeah, I'm gonna mix that up every time, sorry. But soon I'll actually suppress S. Yeah, there will be no more S. So to make it look, well, okay, now I inverted it, but here, this side is clearly this, right? But to make the left-hand side look more like this thing, it turns out that if I take the very group theoretic perspective, this integral is just really integrating over the torus. Well, plus a character like t to the s minus 1. T to the s times the Haar measure. So this is one instance in which an automorphic integral is very successfully related to a null function. Now let me give you a slightly more complicated example, but still in the same setting of modular forms. So this one, so for the people who know, I'm just going to call it constant term, so you expect the answer. So what happens is I still take F a modular form. But this time I integrate it like this instead. So these are pretty much the only two interesting directions you can integrate. And in fact, since I'm rolling the upper half plane up using periodicity, I'm just integrating kind of from here to here. Or maybe I'm going to do from 0 to 1. So I'll integrate from 0 to 1 of f of I plus t. Okay. So if you Fourier expand this, you'll see that only the constant term contributes, which is why I call the example the constant term. So this is just the constant term in the Fourier expansion. Okay. So now we want to relate it to something that's like an L function, right? And if you've seen this type of thing before, you know that the answer is more complicated than just to say it's an L function, because it has two cases. It's two cases. Is zero if f is cuspidal, or is a cusp form. I mean, it's more or less by definition. Cusp forms have constant term zero. But if it's not zero, or if it's not zero, or if f is not cuspidal, then it's something like 2 times zeta. It's not so important what it is, but it's important that it's an L function. Okay, so this is the constant term of the Eisenstein series. So you see that the answer is case-based, but it's still related to some L functions. And I will explain a little bit about how to make it look like the previous thing a little bit later. Are there any
You
questions?
don't have an S on the left-hand side.
On the left-hand side?
Yeah.
So in the second case, it turns out that when it's not cuspidal, then f is Eisenstein. And Eisenstein series have a parameter S as well. So yeah, so basically, yeah. And just like before, I can interpret this completely group theoretically as the integral over the unipotent. So now the left-hand side at least matches what I promised before. Are there any questions so far?
So in what Heck is doing down there on the right-hand side, are you, does this actually construct the Galois representation corresponding to the modular form?
So no, he doesn't construct the Galois representation because this works even when f is not holomorphic. Yeah, but if it were holomorphic and you had attached Galois representation, then it would be that.
Okay, cool.
Yeah.
And over there, are you allowing yourself non-holomorphic Eisenstein series as well as are like for like non-integer values of S, as well as for integer values of S?
Yeah, I think in principle it's okay. Yeah. It's just you might have problem defining L parameter, depending on how far you want to go. Yeah. Okay, so I just want to put these two examples into a pseudo definition proposed by BZSV. So I want to give a reformulation. And this time I'll write out all the names, and after I'll always abbreviate it. So I want to give a reformulation due to them, motivated by TQT. So in the Hecker example, what we want to consider as the starting data is actually, so G is still PGL2. But we want to think of it as acting on a Hamiltonian space or a symplectic space. So the space you want to consider is following. The cotangent bundle of PGL2 mod is the torus. Call this the M. So I don't want to give you the definition of why this is directly related to this, because I actually won't use the definition. But let me just say there's a definition or there's a procedure which you can think of as automorphically quantizing. And it exactly gives you the functional, which is integrate over T. Okay. So without giving you the definition, let me just say, here I have a homogeneous space G mod H, and the answer I got was integrate over H. Right, so in general, without telling you the definition, if M is T star G mod H, then it becomes integrate over H.
So give a reformulation of what exactly of the correspondence?
No, so this is just reformulating what are the ingredients needed to build the integral. So before the ingredient I gave was a subgroup plus a character,
I see.
but they reformulated as it's actually a G space.
Yeah.
Yeah. Any other questions? Okay, so now let me do the dual side. So the dual group is SL2, and I want to think of the starting data to build this L function as the cotangent bundle to the standard representation. So maybe this thing's called M check. And very parallel to above, there is a definition or procedure called maybe spectral quantization. And the thing I get in the end is the L function, the standard L function. So it's just repackaging. And again, let me not tell you the definition, but let me tell you that in general, if M check is the cotangent bundle to a linear representation V, then the answer is the L function.
Sorry, this is supposed to be a relative Langlands correspondence?
I'm about to say the correspondence part. So this part is maybe relative.
What is, I guess what do you mean by the arrow?
These two.
It's like, what do you mean by an arrow from the thing on the left to the thing on the right?
Like from this thing to this thing. So I don't want to tell you the definition because I won't use it.
Okay.
But I'm just telling you to remember that whatever the definition is, in this case, it's
Well, I understand you're not saying the definition, but I mean, what do you even mean by the correspond? Like, do you mean it's a function that sends things?
it's a procedure that takes a Hamiltonian G space and spits out of automorphic function.
Ah, okay,
Yeah.
that's what I was.
Okay, thanks. Yeah, so both the input data is always action on a symplectic variety, and the output is numerical invariant of automorphic form or Galois representation, depending on which side you're on.
That depends on which automorphic form you choose.
Yes. Yeah. So this also depends on the L parameter.
Okay.
Yeah. Thanks.
Oh, the standard is the thing that's on the right over there.
Yes.
Okay.
Exactly. Thanks. Are there any other questions?
So what you had already was a way for taking a subgroup and getting an invariant of an automorphic form.
Yes.
Here we're getting an action on a symplectic variety and getting an arrow.
Yes. Yeah. And the definition is rigged so that those two match. Yeah.
Great.
So, I mean, literally nothing happened. Like you just made a definition to repackage a calculation. But I would say one of the main immediate numerical consequences of PDSV is duality. So the new ingredient is duality, which is we realize that since the input data now is very symmetric, right? Before the input data is like subgroup plus character or linear representation. So one doesn't make sense on the other side, but now both sides are actions on symplectic varieties. So I can forget that this first line had anything to do with automorphic forms and pretend it's on the Galois side. And on the second line, I can pretend it had nothing to do with Galois side and it was automorphic. So let me just write what I would do what I would get if I did that. So I would still let GVPGL2 acting on T star T mod PGL2. And then apply now the spectral quantization arrow. Then it turns out that the answer is exactly, it's 0 unless the L parameter is in T, and the T is the same T as here. So, and if it is, if my L parameter is in T, then it acts on the Lie algebra quotient of these two groups. So I would get the L function of the Lie algebra quotient. So again, I'm not telling you the definition, but in general, if I take a homogeneous space like this, then the spectral quantization formula spits out a case-based answer. It's always 0 unless the parameter was special, being in the stabilizer group. And when it is, then I take the L function of the Lie. And so now maybe you see where I'm going. I take the second line, I let it act on standard. And now I do the automorphic version of the quantization. Then the answer for this is essentially integrating over the unipotent. So, well, in this case, by dualizing, we saw that we got the second example. So it's again an example, an integral that we already understood, but we see that
This L parameter is in T mean.
it just means, so the L parameter is a homomorphism from the Gallo group into G, and I'm asking for it to be actually in T.
How do you see that it is the integral over U? It doesn't follow from the in general statements that you wrote before.
No, so but one heuristic is that the generic stabilizer in this representation is exactly unipotent matrices. If I take the vector 1, 0, then the stabilizer is this group. So it should be related to the integral over that. And in the homogeneous case is literally that. I'm not sure if I answered the first question. Did it make sense?
So this is really the special case where somehow the dual group is more or less the same as the original algebraic group.
No, so I'm now, so in this thing, I'm really taking L parameters valued in PGL2. Right, and I'm asking for the L parameter to be Toro, which is the same as asking for the automorphic form to be Eisenstein. Yeah, so yeah. So let me summarize the moral of the story, or the moral of what I tried to tell you now is that if I try to compute the automorphic period of M, and I relate it to the L function coming from M check, then these type of formulas should always come in pairs. So I should always get something like the following. So this is the expect, or this is the relative duality. At least at the numerical level. Questions about this?
Sorry, I don't understand. So are you saying if you have a Hamiltonian G space, there are some two different notions of quantization
Yes.
that you can associate to any Hamiltonian G space? And they specialize to this or something? I don't know what the statement is.
Exactly that. There's two ways to quantize it. One
Any Hamiltonian G space. It's not,
let's say not every, but a big class of Hamiltonian G spaces. Yeah. So one way will have something to do with automorphic forms, and the other will have something to do with L parameters. But yes, the input data is just Hamiltonian. What was M? M action of P, and M check has an action of G check. And these are, let's just say, symplectic varieties with G action. So now I'm going to switch gears and talk about, now I want to go to the one prime. So you can forget about automorphic forms and L parameters if you don't like them. But remember that there was symplectic action. Okay. So okay, well, I'll just say verbally that the version of the relative duality conjecture I presented for you here is completely numerical. But if you're a type of person that really likes sheaves, then you can ask me later and you can say it all in sheaves. But I think this version is, well, is very pleasing to me. Okay. One of the advantages of seeing it at the sheaf level is now you can apply it to various contexts. So you can apply it to number fields if you're brave enough, function fields definitely, complex curves. You can apply it to topological surfaces, topological three manifolds, depending on what you care about. Okay. So now let me go to the second part, or one prime, about Hitchin moduli space. And for this part, let me just say G is GLN for simplicity. But you can probably guess the general definitions if you'd like. Okay. So let me define this space for you. So let me fix sigma. It's a curve. So let's say over complex numbers. So this is a moduli space of rank n bundles with some extra structure. And depending on who you are, it has various guises. So I'll write 3 of them. And so hopefully one of them is something that you like. So the first one is due to the original work of Hitchin. So you can think of it as solutions to self-duality equations on sigma times R2 that are invariant, translation invariant on the R2 direction. So this definition is due to Hitchin. But it's also the cotangent bundle to the moduli stack of G bundles on the curve. And finally, let me give you a very concrete description. The pair E phi, where E is a rank n bundle on sigma, and phi is a one form valued in the endomorphisms of your bundle. Size. So roughly speaking, this extra phi is responsible for the cotangent direction. And of course, I can forget phi, remember E. That would be the projection to the zero section. So here, this thing is called the Higgs field.
These SD equations are defined for any group G.
Yeah. You can always kind of reduce to this case by picking a faithful representation, and then the equations will yeah. Okay. So this space might look complicated. Well, Bungee is already complicated. It's the cotangent of it, so you might think you made it even more complicated. But actually, it's way, way easier. And I'll tell you the most important map on this space that you need to know. So let's take, if I have a Higgs bundle, then what I can do is I can take the characteristic polynomial of its Higgs field. So if you think about it, you'll realize that this is a polynomial in one forms, but it will have various degrees, right? So the space it will lie in is actually the direct sum of 1 to n A0 in well, right. It's no.
Can I ask a stupid question?
Please,
I think I've asked this before to someone, but what's the difference between bungee and BG?
So BG is point mod G.
Yeah.
Bun G is of the curve. So it's G bundled on the curve.
Okay, but so what if I take BG over the curve? That's something different.
Well, that's something different.
Yeah, okay.
This is more like the mapping stack from the curve
Okay,
to BG.
okay, yeah.
Yeah.
Thanks. If you were to take like bungee of a point, that would be BG.
Yes. Yeah, maybe that's a better answer. Bun G of a point, it would be BG.
Yeah, okay, yeah.
And so you're working with the stacky version of everything, no stability condition.
I think the easiest way for me is to use the Saki version because when I want to do duality, stability, I'm not sure how to translate stability. Yeah, but at this level, you can use stability conditions. Yeah.
But when you talk about solutions to the Hitchin equation, those will correspond to polystable.
Yeah.
But I guess it is like the restriction from X to a point of BG.
Yeah, it's like you integrate out X. Yeah. Okay. Let me call this map chi because it's taking the characteristic polynomial. But does this make sense? This part. I have a matrix whose entries are one forms. I take the characteristic polynomial, so I get n entries, right? But on the ith one, it'll actually be valued in k to the I because it's a degree I polynomial in the one form. So it lies in this. And this space, this is just an affine space, and let me call it A. So this is called the Hitchin base. And so why are Higgs bundles so much easier than just bundles? Is because the fibers of this map are very easy to describe most of the time. Let's give a description of the fiber. So I have a polynomial whose coefficients are in the cotangent bundle, which means that I can define curve inside the total space of the cotangent bundle just by taking the vanishing locus of that polynomial. So this is the vanishing our poly or of A, say. And since A is a degree n polynomial, generically you expect it to be a degree n cover when you project to the base. And this curve is called the spectral curve because it records the eigenvalues of the Higgs field. So for every point in the Hitchin base, you get a spectral curve, branched degree n cover. And the main theorem in the setup is called the BNR correspondence, which gives an interpretation, a moduli interpretation of the fibers. This, yeah, so. Beauville, Narasimhan, Amana. So they say that basically all the fibers are tori. Or generic. Okay. So this Hitchin moduli space looks more or less like this. I have the Hitchin base, and then over it is a bunch of tori, where they're not just random tori, they're Picard groups of these spectral curves. Any questions about that?
So these spectral curves are projected.
Yes, yeah. So now I'm gonna tell you what happens when I consider G check. So far everything is just about G. Now I'm gonna look at the Langlands dual group, and I can still build Higgs G check. And we'll still have the Hitchin, well, this is the Hitchin vibration. So I'm not exactly sure who to attribute this to, but certainly the following names are involved. Gayoto and Witten. Donagi, Pontev, and Hausel Thaddeus. The summary of this is that Higgs G and Higgs G check are SYZ mirrors. So if you know what that means, then great. If you don't, then I will draw basically a picture like this. So what they say is that you can take Higgs G, you look at its Hitchin vibration, and you look at Higgs G check, and you look at its Hitchin vibration. Then there's a canonical isomorphism between their Hitchin bases. So they're really vibrating over the same space. Maybe I'll call this one I. And now if I pick a point, a generic point A, then over it I have a part of A. So over here I can pick the same point, and I would get something like check. Okay. And their picture is basically saying these two are dual tori. So,
So are you omitting sigma in the notation, like xg of sigma?
yeah.
Same sigma.
Same sigma.
And CA is an element or a subset? I mean,
It's a fiber of the map. Yeah, sorry. Right. So in other words, Higgs G and Higgs G check, they're basically fiber-wise dual tori. And the picture that I saw somewhere, which I don't remember now, where is that, so if this is Higgs G, then small tori are big to dual tori. So you can draw a big one here, and then they kind of shrink to the ends. This is like Higgs G check. And they fiber over the same space.
In what sense are the two tori dual to?
So yeah, so it means that if I look at this one, for example,
Yeah.
I can take moduli of line bundles on this general for abelian variety. So I take an abelian variety, I took look at moduli of line bundles, now we get the other one. Yeah.
I have another question.
Yeah, please.
So why is the fiber living in the tangent bundle of the curve? The fiber I inverse of A. You said,
This?
yeah, you said.
No, sorry, this is that's not a mathematical arrow, it's a squiggly arrow. Meaning from this, if I want to describe the fiber, I can take the base point and form the curve.
Oh, okay.
Yeah, and then the actual fiber is Picard by this theorem. Yeah, yeah, thanks. But I mean, this is not, once you realize it's not very difficult, I just push forward basically the line bundle onto my curve. It's degree n, so I get a rank n bundle. And since it was living in the cotangent fiber, I get kind of the eigenvalues of the Higgs field.
Sorry, how do you recover phi from a point of the big CA?
You can't. You can only recover its eigenvalues after permutation.
Is that?
Okay. So let me tell you the main theorem that's yeah, due to Donaghy and Pantev in this context. So I have two spaces and they fiber over A, and the fibers are dual tori. So I can relatively do Fourier transform. So fiber-wise, I do Fourier transform. And it should give me a map from quasi-coherent sheaves on Higgs G. Fourier Mukai to quasi-coherent sheaves on Higgs G Chen. Fiber-wise, Fourier Mukai. Then their theorem says that this is an equivalence generically on the base. The problem why you have to say generic is just because there will be special points in the base where the fibers are not actual tori. So you can't Fourier Mukai, so it's not defined. It's not real like they could have proven it, but they didn't. It's because there's no actual functor over the whole thing. So to emphasize that it's generic, I'll just draw a 0 here. But all you have to remember about this thing is that it comes from Fourier Mukai transform. And the only real thing we know about Fourier Mukai transform is that it sends line bundles to points and vice versa. Right? So it sends like basically a pure wave to the frequency that it came from. So I have a line bundle on a fiber. And it goes to a point, the point of its moduli. So in the in the Langlands context, the original Langlands context, this is kind of like Heck-Huygens sheaves get sent to its L parameter. But now I will ask you to remember that we wanted to start with Hamiltonian or symplectic varieties of G action. So let me in the BZSV setting, if I give you G acting on M, so from this I made an automorphic functional. And from this I also made like an L function object. So L function. And now I want to tell you what that looks like in this context. So this is people call it classical limit. I again give myself G acting on M. The first thing I'll call A of M because it's somehow on the A side and it's supposed to be related to this automorphic quantization. What this is is, maybe I need more space. The data of a Higgs bundle, so I is a Higgs bundle plus a section S. So this S is a section over the curve of that E bundle, that G bundle where I change the fibers into M. Okay, so we're getting the Higgs field for a second. If I have a G bundle, I can just replace the fibers all by a variety that G acts on. This. And then I can use the moment map. And I ask the moment map applied to that section is the Higgs field. So there are some lies in this because I don't want to go to too much detail, but I'll give you an example that basically says all the important stuff. Yeah, maybe later. So this definition was essentially already introduced by Gayotto. So in his paper called duality on boundary conditions. And then later it was made mathematically formal by Ginsburg. Rosenblum in their paper called Gayotto's Lagrangians, something like that. Okay. But whatever this thing is, maybe the most important thing to remember about it is that it maps to Higgs G. Just by forgetting the section. Are there any questions about this? Well, similarly, and this is supposed to morally be related to the L function stuff, let me assume that M is of the form cotangent of representation. So you can define it more generally, but for now, let me give you in this case, which was also realized by Gayotto. Then we want to consider this object called Bm. And it's really just the, people call it Dirac-Higgs complex, because I take homology in the curve of the Higgs field. Side quasi-coherent sheaves. Any questions about this definition?
V times K. What is K?
K is the canonical. Sorry, I forgot one ingredient, but just to make it the definition correct, you have to take the exterior algebra on that. So I don't think I have too much time to explain why you take this definition or this one, to be honest. But when I first saw this in Gayotto's thing, I didn't really understand it either until I realized that it's actually supposed to be related to functions. So let me give a very hand-wavy thing to tell you why this side of the board and that side of the board are the same or are related. So on the A side level, this is basically goes under the name of microlocal support. In words, this automorphic functional is represented by some sheaf, like a D module. Then you can take its microlocal support, you get a Lagrangian, and that's Gayotto's Lagrangian. On the L function side, roughly speaking, this is non-abelian Hodge theory. So there's a non-abelian Hodge correspondence that will take basically things on a local system to things on Higgs. And under that correspondence, L functions correspond to these E of M's. Are there any questions?
Can you explain that a bit? You said the L functions
correspond to these B of M's. It means that there's in nice situations, there's a functor taking this sheaf, which is a coherent sheaf on loc G.
Sheaf, not L.
Yeah, so if you look at the geometry, yeah. But roughly speaking, they're related. They're related by non-appealing diversity. Okay. So in the rest of the time, I said a lot of nonsense, but then I want to show you one computation that convinces you that actually is all very easy. Okay. I'll show you two numbers that that match, and then yeah, and we'll call it a day. But if you have any questions about that, feel free to ask whenever.
Not T star V. There is no description of this.
If there's no description like T star V,
No, here you assume M is T star V.
yes.
If it's not,
If it's not, then in some cases I can define it. In other case, yeah, in other cases I can't. Basically, if the shape of M looks like something that BCSV considers, then I can. So I told you previously that the Higgs bundles, they map to a base and the fibers are tori. But let me take the very, very simple case where that torus vibration is actually trivial. And that happens exactly when G is GL1. So in this case, it's very nice. Higgs G sigma was just a line bundle plus phi, which is a one form valued in endomorphisms of L. But endomorphisms of L are O, so it's just one form. So this space is just T star. And well, this is an abelian variety, so its cotangent bundle can be trivialized, and I can literally write it as pic times one forms. And projection to the one form is the H. So you see that the fibers are tori. And well, the dual of GL1 is also GL1, so the dual H space is the same. So this Donagi-Pantev theorem or functor, it just reduces to the Fourier-Mukai transform from quasi-coherent sheaves on PIC to quasi-coherent sheaves. Outright PIC check, but they're really the same thing.
So pick is the relative Picard stack.
Yes. Yeah. So really, this is fiber-wise over projection to this. But yeah, maybe I'll write that. It's not doing anything in the second component. Okay, so let me give you a flavor of what these A of N's will look like. Yeah. So let me give you a Hamiltonian G space, so G acting on T star of A1. So if you've seen some of this before, then you know that the dual actually is also the same shape. And you might know it under the name of its thesis, duality. Or I later found out from physics people, which I don't understand why, they call it like particle vortex duality. This will be my M. This will be M check. So let's try to compute A of M. And I'll just copy the definition. What it is it's going to be a line bundle, a Higgs field, or one form, plus two sections, S plus and S minus. So inside L plus minus of k half such that s plus times s minus is my one form. So in other words, I'm just asking to factor my one form into two pieces. That's all. So very heuristically, you see that if I have zeros of phi, then they have to be either s plus or s minus will have to be responsible for it. So I see that the zeros of phi will be the zeros of s plus, showing you the zero of s minus. So how many ways are there to do that? Well, it's just to split it into two pieces. It's 2 to the 2g minus 2. So this is the heuristic justification for A of m when you map it to Higgs. Fiber-wise, it's just 2 to the 2g minus 2 points. So I have this many points on A. And what about, okay, yes, well, are there any questions?
K to the 1/2.
Yeah, so this whole story depends on spin structure, but I decided to not worry about it.
So does that come from the moment map?
It does come from the moment map. Yeah. So my goal is to show you that that number appears in B. Yeah. So here I'm trying to take the cohomology of this complex. And the only interesting part is in H1. So I look at this and take exterior algebra. Well, if phi is generic, then this just is the co-kernel of phi. And the co-kernel of that is whenever phi vanishes. Right, so it's really the exterior algebra on the direct sum. With a 0 of phi. But now you see that this has 2g minus 2 lines. And I take exterior algebra. So the rank of this is 2g minus 2. Yeah. And I hope that's somewhat convincing that the Fourier transform of these points becomes a direct sum of the same rank of line. So I think I'll stop there. Thank you, Origin.
Are there questions for Eric?